Lesson: Inferential statistics for AI applications. Inferential statistics plays a pivotal role in AI applications, providing the means to draw conclusions and make predictions based on data. This aspect of statistics is essential for AI professionals who aim to develop models that not only describe the past, but can also predict future outcomes and inform strategic decision-making. At its core, inferential statistics involves the analysis of a sample from a population to make inferences about the population itself. The two main areas of inferential statistics used in AI hypothesis testing and estimation enable data scientists and AI practitioners to make informed decisions and validate models. In AI applications, hypothesis testing is a fundamental process for determining whether a certain premise about a dataset holds true. For example, suppose a company is testing whether a new AI-driven recommendation system increases user engagement compared to the existing system. By employing a hypothesis test, the company can systematically assess whether observed differences in user engagement metrics are statistically significant or merely due to random chance. The process involves formulating a null hypothesis, which in this case might state that there is no difference in engagement between the two systems, and an alternative hypothesis stating that the new system results in higher engagement. Subsequently, a test statistic is computed and a p-value is derived to help decide whether to reject the null hypothesis. Choosing the appropriate test is crucial for accurate results. Commonly used tests in AI include the t-test for comparing means and the chi-square test for categorical data. For example, a data scientist might use a t-test to determine if an AI model's predictions significantly differ from actual outcomes over multiple trials. The choice of test depends on factors such as data distribution, sample size, and whether data points are paired or independent. In practice, AI professionals often rely on software tools like Python's SciPy or R's statistical packages, which provide built-in functions for conducting these tests efficiently. Another critical component of inferential statistics in AI is estimation, which involves determining the value of an unknown population parameter based on sample data. Point estimation and interval estimation are two types of estimation techniques. Point estimation provides a single value as an estimate of a parameter, such as using sample mean to estimate population mean, while interval estimation provides a range of values known as a confidence interval, within which the parameter is expected to lie with a certain level of confidence, typically 95%. Confidence intervals are particularly useful in AI applications for assessing the precision of model predictions and the uncertainty associated with them. For example, when deploying an AI model for sales forecasting, a confidence interval can help stakeholders understand the range within which they can expect future sales to fall, thus aiding in inventory and resource planning. The integration of Bayesian inference in AI has gained prominence due to its ability to incorporate prior knowledge and update beliefs with new data. Bayesian methods are especially useful in AI applications where data is sparse or noisy. For instance, in medical diagnosis, Bayesian inference can improve decision-making by combining historical data with current patient information to assess the probability of a disease. Tools like PyMC3 and STAN allow practitioners to implement Bayesian models and perform complex calculations that would otherwise be intractable. Real-world AI applications often involve complex datasets with multiple variables and potential interactions, making multivariate analysis another crucial aspect of inferential statistics. Techniques like multiple regression, factor analysis, and principal component analysis enable the exploration of relationships between variables and the reduction of data dimensionality. Multiple regression, for instance, allows AI practitioners to model the relationship between multiple independent variables and a dependent variable, providing insights into which factors significantly influence outcomes. PCA is widely used for feature reduction, improving model performance and interpretability by transforming high-dimensional data into a lower-dimensional space while preserving variance. The application of inferential statistics in AI is not without challenges. One significant issue is the risk of overfitting, where a model becomes too complex and captures noise rather than underlying patterns. Regularization techniques, such as lasso and ridge regression, are frequently employed to mitigate overfitting by adding a penalty to the model complexity. Cross-validation is another vital strategy used to assess model performance. By partitioning the dataset into training and testing sets, practitioners can evaluate how well a model generalizes to unseen data, thereby ensuring its robustness in real-world scenarios. AI professionals also face challenges in ensuring the ethical use of inferential statistics. Misinterpretations of statistical results can lead to biased decision-making and perpetuate existing inequalities. For instance, if an AI model is used for hiring decisions and is trained on biased historical data, it may reinforce discriminatory practices. Therefore, it is imperative for AI practitioners to not only possess technical proficiency in statistical methods, but also a keen understanding of their ethical implications. Implementing fairness-aware machine learning algorithms, which adjust model predictions to account for potential biases, is one approach to address this issue. In conclusion, inferential statistics is a cornerstone of AI applications, enabling practitioners to make data-driven decisions and build predictive models that are both effective and ethical. Through hypothesis testing and estimation, AI professionals can validate their models and quantify uncertainty, while Bayesian inference and multivariate analysis offer robust frameworks for tackling complex datasets. By leveraging statistical software tools and frameworks, such as SciPy, PyMC3, and STAN, professionals can efficiently apply these methods to solve real-world challenges. However, the responsible application of inferential statistics also requires a commitment to ethical standards and a continuous effort to mitigate biases and ensure fairness. As AI continues to evolve, the integration of advanced inferential techniques will remain crucial for unlocking actionable insights and driving innovation in various domains.